Now we will start with the next chapter, and that is mechanical properties of solids. Okay, we'll start with mechanical properties of solids. So, see, what are the types of bodies? Okay, what are various kinds of bodies? So, the kind of bodies that we have studied till now, they are known as rigid bodies. And what are rigid bodies? So, rigid bodies are the bodies which won't have any change in their shape or size or both, okay, due to the application of external force. So external force will only result in the change in motion of the body, not in its shape or size. Okay, so those bodies, they are known as rigid bodies. The next is elastic bodies. So what is an elastic body? So when you apply an external force, the body will get deformed. Okay, what is deform? What does deform mean? So deformation means change in shape or size or both. Change in shape or size or both. Okay. So when you exert an external force, so because it changes the shape or size of body, it is known as deforming force. Okay. So when external deforming force acts on this kind of body, I wrote elastic. It is elastic. Okay, external deforming force acts on an elastic body. The body gets deformed, but once you remove that external force, there is a restoring force generated within these kind of bodies which will restore it back completely. Okay, which will restore it back completely. So body will regain its original shape and size once the external force is removed. Okay, so that kind of body is known as elastic body. Okay, and then we have, so this is perfectly elastic body. Then we can have partially elastic body and plastic body. Okay. So what is plastic body? So for plastic body, when you exert an external force, the body will get deformed, and when you remove that force, the body stays deformed. Okay. So if shape or size of this body is changed, it will remain as it is when you remove the external force. What is an example of elastic body? We can say rubber is fairly elastic body, right? Then lump of mud or clay, it is a plastic body. Okay, an example of plastic body. But actually, in practice, nobody in the world is perfectly elastic or perfectly plastic. Okay, it is somewhere in between. So the bodies which are not perfectly elastic and not perfectly plastic, which most of the bodies in the world are, okay, they are known as partially elastic bodies. They are known as what? Partially elastic bodies. So when you exert an external force on any real body, it will regain its original shape up to some extent, and there will be some deformation left, okay, in the most of real world bodies. So those bodies are known as partially elastic bodies. So perfectly rigid body does not exist. This is an idealization. For simplicity, we consider that bodies are rigid. Okay, when we want to study motion of bodies, then we consider that bodies are rigid. Okay, so the external force will bring out the change in only motion of the bodies, not in their shape and size. Because we want to study motion, we neglect the change in shape and size. Okay. Now we don't want to study motion of bodies. We want to study their elasticity. So in this case, now when we exert an external force, okay, it changes the shape or size of body, right? So the bodies which regain their original shape and size completely, they are known as elastic bodies. Bodies which don't regain their original shape and size at all, okay, they are known as plastic bodies. And the bodies which regain the original shape and size or both up to some extent, they are known as partially elastic bodies. So these are types of bodies in general, but number one and number one and number two and number four also, these are idealizations. Okay, so no body in the world is perfectly rigid or perfectly elastic or perfectly plastic. All bodies, they fall under only this category, that is, they are only partially elastic bodies. Okay, but we can give some examples. So for an example, rubber, steel, etc., these are almost perfectly elastic. Okay, so they are almost perfectly elastic, we can say. So these are often given as examples of elastic bodies. Okay. And uh, for an example, clay, then wax, etc., these are almost perfectly plastic. All right. Then the property of bodies by virtue of which they regain their original shape and size, it is known as elasticity. Okay, so what is elasticity? It is the property of bodies by virtue of which they regain their original shape and size. Now, what is the reason of this elasticity? Okay, where does this elasticity comes from? So, for an example, let us suppose we have a string. Okay, so this is a string. Suppose this is some string, okay, or wire, and it is connected to this rigid support, and some weight is hung from this wire. Okay, so suppose this is the weight that is hung from this wire. So now what happens? So this weight acts downwards, it is mg. So what is this wire consisting of? So what is there inside this wire? There will be, if it is made up of some metal, okay, which is in element form, then there will be atoms inside it, right? So if you zoom this wire, what is there inside the wire? There are atoms. Okay, so not 2, 3, 5 atoms, there will be millions of atoms. And these atoms are separated by a fixed distance. It is known as equilibrium distance. Okay, so why are they separated by a fixed distance? It's because of it is the distance at which the electrostatic forces are balanced. Okay, so we know that atoms are made up of positively charged nucleus and negatively charged electrons. Okay, so these red circles that I have drawn, these are the nuclei. Okay, these are positively charged, and electron clouds are negatively charged. Okay, so now when you bring two atoms close to each other, what will happen? What kind of forces will act? So there will be the force between these negatively charged electrons and negatively charged electrons. So they will repel each other. This nucleus and this nucleus, they will also repel each other, right? But this nucleus and these electrons, they will attract each other. And this nucleus and these electrons, they will also attract each other. So now what happens is, so there is some force of repulsion due to electrons and nucleus and nucleus, and there is some force of attraction between what? Electrons and the nucleus, electrons of one atom and nucleus of other atom, and vice versa. Okay, so the atoms, they get stabilized at a particular distance. What will be that distance? Where this repulsive force and the attractive force is balanced. Okay, so at that distance the net force will be zero. So atoms, they like to stay at that particular distance from each other. Okay, so that distance is known as equilibrium distance. So whenever you exert some external force, what will happen? So now you are stretching this wire. Okay, when this weight is hung from the wire, it is stretching that wire, right? So the interatomic distance will increase. So when the distance increases, there will be an attractive force developed between the atoms. Okay, so the forces between atoms, they are like springs. Okay, the bonds between atoms, we can say, they are like springs. So we can imagine all of these atoms, they are connected by springs. Okay, so not literally, they are not connected by springs. So bonds between the atoms, okay, they behave like springs. So the forces behave like springs. Okay, so that means when you stretch a body, what happens? These bonds get elongated. So the restoring force will try to uh, it will try to decrease the distance. Okay, so the atoms will attract each other, and if you compress it, what will happen? The atoms will repel each other. Okay, so when you stretch a body, what will happen? The interatomic distance will increase and an attractive force is developed. Okay, so this is the reason. The interatomic forces between the atoms is the reason of elasticity. You got it? Yes, no? So there is a particular limit up to which you can stretch a body, and it will have the body will have its elastic properties. Okay, there is a particular limit up to which you can stretch a body and body will remain elastic. So that limit is known as elastic limit. Okay, so there is particular value of external force that can be exerted on body such that it remains elastic. Okay, so that maximum external force, actually maximum external stress that you can apply on a body and it remains elastic, it is known as elastic limit. Okay, so we'll talk about that, but before that, let us define stress. Okay, so what is stress? All of us know, right? When exam is near, okay, we get stressed, right? There is lot of pressure. Okay, we get stressed. So what is stress? This is our day-to-day language stress. Okay, so stress is defined as, it is defined as internal restoring force per unit area. Okay, so we have just discussed that when you exert an external force on a body, what happens? The interatomic distance between body interatomic distance between the atoms of bodies, it gets changed, and because of that a restoring force is generated. Okay, so that is internal restoring force per unit area is known as stress. Okay, so now till the time body is elastic, that internal restoring force is just equal to the externally applied force. Okay, how much will be the internal restoring force? It is just equal to the externally applied force till the time body is elastic. Okay, so in general we'll take internal restoring force equal to the externally applied force, right? So stress is defined as internal restoring force per unit area. So now, depending upon various situations, there are three kinds of stresses. Okay, so first one is known as longitudinal stress. So what is longitudinal stress? So now, for an example, in this example, so here we have a wire. This wire will have some cross-sectional area. Cross-sectional area is suppose A, and we have connected this load on this wire. So what happens because of this load? It changes the length of this wire. So when the external deforming force changes length of an object, okay, then the stress generated is known as longitudinal stress, right? When the external deforming force, it changes length of an object, then the stress generated within the object, it is known as longitudinal stress. Okay, simple definition, right? So how much is longitudinal stress? So stress is denoted by this letter sigma. Okay, and it is equal to internal restoring force F divided by area A. And as I said, how much would be the internal restoring force? It is just equal to the externally applied force. Okay, the body is elastic. So this is equal to mg upon A. Okay, so this definition is clear. So this is longitudinal stress. Then next is volume stress. Okay. So suppose we have some liquid, okay, some fluid actually, and so let me draw it. So suppose we have this fluid tank. Okay. So we have this water tank and a ball, some metal ball is immersed in water. Okay. What will happen? This fluid will exert some pressure on it from all sides, and due to this pressure, what happens is the volume of this ball decreases, right? So this ball experiences pressure from all sides. So now if applied force, if external force results in decrement in volume, change in volume of an object, the stress generated in the object, it is known as what? Volume stress. Okay. So see, this force is acting equally from all sides. Okay. So now force upon area can be called as pressure. Okay. So volume stress is equal to what? So volume stress is equal to what? this normal force which is acting from all sides divided by area, or you can just call it P. What is P? P is the pressure. So volume stress is also known as bulk stress. Okay, it is also known as bulk stress. Fine. So because it acts on all sides in bulk, you can say, okay, so it is known as bulk stress, or because it changes volume of a body, it is known as volume stress also. And how much is it equal to? It's equal to the pressure. Okay, so pressure which is acting from outside, it will be equal to internally generated pressure, right? So the internal restoring force per unit area, it is known as what? Stress. Okay, so this is definition of volume stress. This is clear. And there is one more, it is known as tangential stress or shear stress. Okay, and the meaning is clear from the name itself. So now in this case the force will act tangential to the area, and now you place your hand on that book. Okay, so you place your hand on this book and you slide your hand. What happens? So the bottom layer of the book, the back cover of the book, it is in contact with the floor, so it remains as it is. But the top cover over which you are pressing your hand and sliding it will slide a little bit, right? It will slide a little bit. Okay. So in what direction are you applying the force? You're applying the force tangential to the area of top surface, right? So this force divided by area of the top surface, it is known as shear stress or tangential stress. Okay. So shear stress is defined as tangential force per unit area. Okay. Another example. So let's suppose you have this metal cube and you exert a force on top layer. Okay, not top layer. You exert a force on top surface. So you hammer that top surface. What will happen if you hammer the top surface? So let's suppose bottom surface is fixed. Okay, so this top layer, it gets shifted. Okay, it gets shifted from here to, suppose, this new position. So top layer gets shifted like this. Okay, so not only the top layer, the layers below it, they will also get shifted, right? So the bottom layer remains fixed and the other layers get shifted relatively. Okay, so the cube now becomes like this. Okay, so cube was like this earlier. You're hammering the top surface, so you're hammering tangential to the top surface, so it becomes like this. It gets tilted like this. Bottom layer is fixed, other layers, they get shifted. Okay, so okay, so in this case the force acting, it is on this top layer. Okay, so force acts on this top layer only. Okay, and that means it is acting on this area of the top layer. So this force divided by this area is known as the shear stress. It is known as shear stress. Voice is breaking. Now also is it breaking? So now related to these three stresses, there are three strains. Okay. So what is strain? Okay, so let's define this quantity known as strain. Strain is defined as change in configuration, some configuration of body per unit original configuration. Okay, per unit original configuration. Okay, so this is some quantity, either you can say length, okay, volume, etc., etc. Change in configuration per unit original configuration is strain. Okay, so what will be dimensions of strain? It is dimensionless, right? If you take change in length upon length, it's dimensionless, right? So based upon three types of stresses, there are three types of strains. Okay, so what are three types of strains? First one is longitudinal strain, and it is equal to what? So strain is denoted by this letter epsilon. Okay, so what is longitudinal strain? It is change in length per unit original length. Change in length per unit original length of wire. So it is delta L divided by L, you can say. This is longitudinal strain. Okay. Similarly, there is volume strain. So what is volume strain? It's equal to change in volume per unit original volume. Okay. And next type of strain is shear strain. So what is shear strain? So see what happens when you apply shear stress on a body. Shape of body changes. Okay. So this top layer, it gets shifted by some distance. It gets shifted by this much distance, let's suppose. So this shift is equal to x. Okay. So this much shift is equal to what? It is equal to x, right? And this much length is L, suppose. Okay. So what is shear strain? Shear strain is defined as shift in position of top layer divided by its distance from fixed layer. Okay, it is defined as shift in position of a layer divided by the distance of that layer from fixed layer. Okay, so it is this x, shift in position of a layer divided by its distance from fixed layer. Okay, which is L. Okay, so shear strain is defined as x upon L. Okay, but let me just write it. Shift in a layer divided by its distance from a fixed layer. So shift in position of a layer divided by its distance from fixed layer, and it is equal to what? X upon L. So it is equal to x divided by, sorry, L. Okay, this x upon L. Okay, so this angle by which this layer gets shifted, okay, the angle by which uh, the layer gets shifted, it is known as angle of shear, theta. So theta is known as what? Shear angle or angle of shear. So what will be x upon L in terms of this angle theta? It is tan of theta. Okay. What is x upon L? It is equal to tan of this angle theta. So just shear strain is defined differently than that of longitudinal or longitudinal, you can say longitudinal or volume strain. Okay. So this definition is little bit different. Okay. So then we will discuss one more thing, and it is Hooke's law. So Hooke's law we have discussed earlier. Actually, Hooke's law we have discussed twice. Okay. So what is Hooke's law? Force is directly proportional. The restoring force is directly proportional to what? The displacement. Restoring force generated in a spring or any body, the restoring force is directly proportional to the displacement. It's directly proportional to the displacement, right? This is the Hooke's law that we have studied. Okay, so this force can be divided by area. Okay, for small displacement we can say area of cross section remains constant. Okay, it remains almost constant, we can say, for a small displacement. And right hand side, if you divide by L, then you get on left hand side it's force upon area, restoring force upon area, that is stress. Okay, stress. And on right hand side you have strain. On right hand side you have strain. So this is longitudinal stress and this is longitudinal strain, but it is valid for all kinds of stresses and strains. Okay, so what does the Hooke's law say? It says under the elastic limit, under the elastic limit, stress is directly proportional to the strain. Okay, and the proportionality constant between the stress and strain, it is known as modulus of elasticity. Okay, so stress is equal to, we can say, so if we remove this proportionality sign and put an equality sign, constant will come. Okay, we have to write a constant. Constant is denoted by E and it is known as modulus of elasticity. Okay, so what is E? E is the ratio of stress to strain. Right, if you take strain on the other side, it is the ratio of stress to strain. Okay, and it is known as modulus of elasticity. Okay, so what is Hooke's law? Under the elastic limit. What is elastic limit? It is the maximum value of stress which can be applied on a body. Okay, and body still remains elastic, right? It's elastic limit. So under the elastic limit, stress is directly proportional to the strain. Okay, so we can write stress is equal to this constant times strain, and if we take strain on other side, okay, we get that constant. Stress upon strain is a constant. Okay, and this constant is known as modulus of elasticity. Okay, so depending upon three types of stresses and strains. There are three types of moduli of elasticity, namely Young's modulus, bulk modulus, okay, and modulus of rigidity. Okay, so what is Young's modulus? Young's modulus is denoted by Y, and it is just ratio of longitudinal stress to longitudinal strain. Longitudinal stress to longitudinal strain. Okay. So what is longitudinal stress? Mg upon A. And what is longitudinal strain? So it is delta L upon L. And dividing by delta L upon L is equal to multiplied by its reciprocal. Okay. So Y is equal to what? Mg multiplied by L divided by A multiplied by delta L. So this is Young's modulus. Okay. Next one is bulk modulus. So bulk modulus, I'm sorry, bulk modulus is denoted by letter B. Okay. And it is just volume stress divided by volume strain. Okay. So it is equal to what is volume stress? Volume stress is P, right? It's equal to pressure. What is volume strain? It is delta V upon V. Okay, it is delta V upon V. But here we put a negative sign. Okay, and why do we put a negative sign? It's because when pressure increases, what happens to the volume? Volume always decreases. Okay, when the pressure increases, volume always decreases. So to compensate for the change in sign between pressure and volume, okay, pressure and change in volume, okay, we put this negative sign. Okay, so the bulk modulus B is equal to what? Minus of P multiplied by V upon delta V. Next is shear modulus. So shear modulus is generally denoted by letter G. Okay, and what is it? It is just ratio of shear stress to the shear strain. Ratio of shear stress to shear strain. And it is equal to what is shear stress? So it is tangential force F divided by area. And what is shear strain? It is X upon L, right? So dividing by that is equal to multiplied by reciprocal. Okay. So this is F into L divided by AX. Okay. And it can be also written as, see, this X upon L can be written as tan of theta. So we can write it that way also. So if we write it that way, then we'll have tan theta in the denominator. So F upon A tan theta. Okay, this is shear modulus. F into L divided by AX. Okay, so we have seen some theory. Let us discuss some problems based upon this. and problems will be very simple. So let's start with very simple problem. So this problem, okay, let us start with very simple question. Shearing stress is related to, it is related to change in which thing? Length, volume, shape, area. Tell me. A shape, right? Options C. Okay. Okay. One more thing. Shear modulus is also known as modulus of rigidity. Okay. And why is it known as modulus of rigidity also? It's because, see, shear stress is related to what? Change in shape of body. And what is rigid body? Rigid body is a body whose shape does not change at all when you exert an external deforming force. Okay. So the amount of stress required per unit strain caused. Okay, it is modulus of elasticity, right? So amount of shear stress required per unit shear strain. This is known as modulus of rigidity. It's measure of rigidity of a body. If more stress is required, then the body is more rigid. If less stress is required, that means the body is less rigid. Is it clear? Okay. So shear modulus is also known as modulus of rigidity. Okay. If the angle of shear is 30 degree for a cubical body and change in length is 250 centimeter, then the original length of the cube is. So this is very simple, right? So we know shear stress is given by tan of theta. What is tan of theta? The shift in position of a layer. Okay, or you can say change in length. It's not change in length per se, it is shift in position of a layer. Okay, but they are calling it change in length. So it is x divided by L, and you want to find out L. Okay, so this is very simple, very straightforward. So it is tan of 30 degrees. Okay, so how much is tan of 30? Equals to x upon L, and you want L. So it is x divided by tan of 30 degrees. Okay, so sine 30 is half, cos 30 is root 3 by 2, so tan 30 is 1 upon root 3, right? So this is equal to x is 250 centimeters multiplied by, okay, dividing by 1 upon root 3 is equal to multiplied by its reciprocal, so multiplied by root 3, and all answers are in meters, so let's convert this to meters. Okay, so it is 2.5 meters multiplied by root 3. Root 3 is 1.73. So how much would be 2.5 multiplied by 1.73? Little less than 5, you can say. Okay, so option D, right? It's equal to 4.3 meters. So this was simple question. Next question. This is from NEET 2020. Okay. So a wire of length L, area of cross section A, is hanging from a fixed support. The length of wire changes to L1 when mass M is suspended from its free end. The expression for Young's modulus is. See, this is from NEET 2020. Okay, so recent question. So what is Young's modulus? It is MGL divided by A multiplied by delta L. What is delta L? It's change in length. The change in length is equal to original length is L, final length is L1. So how much is change in length? L1 minus L, right? So delta L is L1 minus L. What is the answer? They have taken M capital. So mgl divided by A multiplied by L1 minus L. Option D is the answer, right? So this kind of simple questions are still being asked. Next question. Two wires are made of same material and have same volume. There are two wires, they are made up of same material, they have same volume. The first wire has cross-sectional area A and second wire has cross-sectional area 3A. If the length of first wire is increased by delta L on applying force F, how much force is needed to stretch the second wire by the same amount? Okay, this is the question. Two wires have same volume. Okay, so volume of two wires is same. So V1 is equal to V2. So now, if this is a wire, this is area of cross section and this is the length of the wire. So volume can be written as this area multiplied by the length. Okay. So now for first wire, you can say it is A1 multiplied by L1, and for second wire, it's A2 multiplied by L2. So L1 upon L2 is equal to A2 upon A1. This is what we get, right? So see, this thing is given. Area of first wire is A, area of second wire is 3A. So this is equal to 3A upon A. Okay, so that is L1 upon L2 is equal to 3. This is given. Okay, I mean this is what we can find out from the given thing. Then we want to find out, actually this thing is given that change in length is same. Okay, if length of first wire is increased by delta L on applying force F, how much force is needed? This is the question. To stretch the second wire by the same amount. So see, we can use this formula y is equal to mgl divided by A into delta L. Okay, and delta L can be written as then mgl divided by ay. Okay, delta L can be written as delta L. If you take it on left hand side, y on right hand side, so it can be written as mgl upon ay. And this is given that delta L1 equals to delta L2. Okay, so in place of mg, let's write F. Okay, because force is given. So let's write delta L1 equals to delta L2. So this can be written as F1 into L1 divided by A1 into Y. Okay, F2 multiplied by L2 upon A2 into Y. So Y and Y will get cancelled because it's the same material. So for same material, Young's modulus will be same. Okay. So Young's modulus does not depend on the length and area, etc. It doesn't depend on dimensions. It is property of a material. Okay, so A and A gets cancelled. So what do we get? So we can move A2 and L2 on left hand side, F1 on right hand side. So what do we get? F2 divided by F1 is equal to, okay, if I move this on right hand side, so it is equal to L1 upon L2 multiplied by A2 upon A1, right? So this is equal to, how much is L1 upon L2? 3. How much is A2 by A1? It is also 3, equal to 3. Okay, so 3 times 3 is 9. Okay, so this gives F2 is equal to what? It is 9 times F1. Okay, so answer is 9 times F. Option A. Is it clear? So let us see next question. The bulk modulus of spherical object is B. If it is subjected to uniform pressure P, the fractional decrease in radius is. This is the question. It's a simple question. Bulk modulus can be written as what? It is pressure multiplied by, okay, volume upon delta V, right? Or we can say it is equal to minus of P divided by delta V upon V. Okay. So we want to find out fractional decrease in radius. Okay, we want to find out fractional decreases in radius. So let's take delta V upon V on left hand side, B on right hand side. So what do we get? Minus of P upon B. Delta V upon V is minus of P upon B. Okay. So now this is a spherical object. What is volume of a sphere? Sphere V is equal to 4 by 3 pi r cube. Okay. So now let's recall from units and dimensions. So delta V upon V will be equal to what? It is equal to 3 times delta R upon R, because V is directly proportional to R cube. Okay. So delta V upon V is 3 times delta R upon R. So I can substitute 3 times delta R upon R over here. It's equal to minus V by B. Now take that 3 on other side. So what do you get? Delta R upon R is equal to minus P by 3B. This is the answer. Okay. Option C. So the minus sign is not there because only magnitude is asked. Okay. How much will be the fractional change in radius? The magnitude of fractional change is asked. That's why it's P upon 3B only. Let's see next question. The Young's modulus of steel is twice that of brass. Two wires of same length and same area of cross section, one of steel and another of brass, are suspended from the same roof. Okay, so roof is also same. If we want the lower ends of wires to be at the same level, we want lower ends of these two wires at the same level, then the weights added to the steel and brass wires must be in the ratio of. So this is simple. Very simple question. Okay. Young's modulus of steel is twice that of brass. So let's use S for steel, B for brass. Okay. So now you have those two wires. Okay. And you hang some weights by those two wires. And you want extension to be same, extension to be equal. See, so extension can be written in terms of Young's modulus like this. Okay. So Young's modulus is F into L divided by A multiplied by delta L. Okay. Y equals to F into L upon A multiplied by delta L. So we can write delta L equals to, okay, if we take delta L on this side, Y on other side, F into L upon AY is delta L. So we want delta L of steel equal to delta L of brass. Okay. So this can be written as FL upon AY equals to FL upon AY. So let's put suffix S, 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 and here B, 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 B. Okay, right? So now what's given? They have same length and same area of cross section. So we can cancel out lengths and area of cross section because it is same. Okay, so then Young's modulus of steel is twice that of brass. Okay, what is given? Young's modulus of steel is equal to 2 times Young's modulus of brass. This is given in the question. Okay, let me read it once again. The Young's modulus of steel is twice that of brass. This is given. Young's modulus of steel is twice that of brass. Two wires of same length and same area of cross section, one of steel and another of brass, are suspended from same roof. Okay, so there are two identical wires, but one made up of steel, another made up of brass. They are connected to same roof. Okay, if we want lower ends of wires to be at the same level, so you want same extension in those two wires. Okay, then the weights added to the steel and brass wires must be in the ratio of. This was the question. Okay, so y can be written as F into L upon A into delta L. So if you want delta L, take delta L on other side, y on right hand side. So delta L equals to F into L divided by AY. Okay, and you want same extension in both the wires. So Fs into, okay, you can write delta L equals to F into L upon AY. So put suffix S for steel and B for brass. Okay, then the wires are identical. That means length and area of cross section is equal. So length and area of cross section can be cancelled out on both sides. Okay, so now Young's modulus of steel is 2 times that of brass. It is given. Okay, so you can cancel out this thing also, but factor of 2 will come there. Okay, so Fs divided by 2 is equal to Fb. Okay, so weights added to the steel and brass wires, they are in the ratio. So Fs upon Fb is equal to what? 2 upon 1. They are in the ratio 2 is to 1. This is the answer. Option D. Is it clear? Next question. The appropriate depth of an ocean is 2700 meters. The compressibility of water is this thing. Okay. So compressibility we're going to discuss tomorrow, but it is just a definition. Compressibility just inverse of the bulk modulus. Okay, nothing else. Okay, so the compressibility of wire is 45.4. Sorry, compressibility of water, not wire. It is this much, and density of water is this much. What fractional compression of water will be obtained at the bottom of ocean? Okay, depth of ocean is given. We want what compression of water will be obtained at the bottom of ocean. So see, this is again, this is simple. Okay, so what is bulk modulus? It is equal to minus of P divided by delta V upon V. You want delta V upon V. Okay, so delta V upon V is equal to what? Minus of P upon B. Okay, minus of P upon B, and 1 upon B is what? 1 upon B is compressibility. So this is equal to delta V upon V is equal to what? minus P upon compressibility is denoted by K or kappa, you can say. Okay, so minus P times K, and pressure can be written as, so delta V upon V is equal to minus of pressure can be written as rho g h, right? Pressure can be written as rho g h. Okay, so we can substitute values now. So density is given 10 raised to 3. Acceleration due to gravity is 9.8. Let's take it 10. Multiplied by height is 2700 meters, 2700. Multiplied by kappa is how much? It is 45.4 multiplied by 10 raised to minus 11. Okay, so this is 10 raised to 3, 4, 5, 6, right? So it is minus of 10 raised to 6 multiplied by 10 raised to minus 11 multiplied by 27 multiplied by 45.4. So approximately, I'm sorry, this will be little bit over 1000. Okay, but options are closed, so you have to calculate it. There is no option. Okay, anyways, so 45, let's skip 4, 45 multiplied by 27. Okay, so how much would be this? 7 fives are 30, sorry, 35, not 30. So 5 twos are 10, 13, 0, then 27 fours are how much? 108. Right? Am I right? I think so. So this is 5. Okay, 1215. All right. So this is 10 raised to minus 11 multiplied by 10 raised to 6. It's 10 raised to minus 11 plus 6. That is 10 raised to minus 5. Okay, 10 raised to minus 5 multiplied by this thing, this factor. So it can be written as 1.215. Okay, 1 point minus of 1.215 multiplied by 10 raised to 3. Right, this thing can be written as 1.215 multiplied by 10 raised to 3. Then we have multiplied by 10 raised to minus 5. So 10 raised to 3 minus 5 is minus 2. So option A is the answer. Right? Yes. Oh, you already calculated. Good. So option A is the answer. Okay. So let us stop here. Okay. And remaining part we'll discuss tomorrow.